Welcome to day one of Related Rates, section 2.7. We are going to do a few examples today that involve circles, spheres, cones, that sort of thing. Yesterday we went over the formulas so that we have those for easy reference in case you should forget. These write the following statements mathematically. I'm going to do this real quickly. Sally is growing at a rate of 3 inches per year. The word rate indicates to me that it is a derivative with respect to time, since it said per year. I'm going to use this S for Sally. Sally's growth rate is 3 and then inches per year. My house is increasing at a value of 10,000 per year. Oh, that's a rate since I see the per year. So I'm going to say DH dt for house. My rate of change is $10,000 per year. The radius of a circle gets larger by 2 inches per minute. That's a rate. It's positive since it's increasing, so I could say dr dt equals 2 inches per minute. The outside temperature is dropping by, dropping's a keyword, by 5 degrees Fahrenheit per year. Or per hour. That would be crazy. Okay, outside temperature. I'm going to go with a T, but I'm going to use capital T for temp, little t for the time. So I've got the change of temperature per change of time. And that's going to be a negative 5 degrees Fahrenheit per hour. So you got to pay attention to whether it's increasing or decreasing. To make sure you get your signs right on your quantities. To solve related rates problems, you really just need a strategy, and that strategy can pretty much be the same on each of these problems. And I've found that this DREADS idea works very well to get you through the steps that should lead to success. I would draw a picture, label it up, get some variables labeled. R stands for rate. Note the given rates and the target rate, what you seek, and then make sure your signs are correct. So if it says the radius is increasing, well then I'd have like a dr dt equals. So I pay attention to what is given and what you're trying to find. Equations, we are going to, E stands for equations. We are going to write an equation that relates the variables that we found in the step with where we took note of the rates. So E for equations. Once we get our equations written, then we can take the derivative. Mostly it's going to be implicit differentiation with respect to time. And then finally we'll substitute and solve. We'll substitute the values of the known quantities in our word problem. All right, so let's get it going. We've done this in class where we blew up the balloon and watched how things changed. A spherical balloon is inflated at 5 cubic centimeters per second. How fast is the radius changing when the diameter is 8 centimeters? So immediately from this, I'm going to think to myself, well, that means the radius is 4 centimeters. I'm going to go ahead and go through this problem. D for draw, I'm going to draw a picture of my sphere. It's got a radius of what, 4 centimeters. So there's my R. I'm going to take note of the rates that were given. They gave us that it was inflated, so that's a dV dt equals 5 cubic centimeters per second. They want us to find how fast the rate of the radius is changing. And that's going to be when R equals 4 centimeters. An equation, I need an equation that will relate. It must relate volume, the radius, and the fact that we have a sphere. Let's get this spelt right. It has a sphere. So what equation would work? Well, that would be the volume of a sphere equation. So 4/3 pi r cubed. D stands for derivative. We are now on the derivative step. So let's take a derivative with respect to time. So I get dv dt equals 4/3 pi, And then 3r squared dr dt was really where the work came in from the r cubed. I'm going to get the 3's canceling, so dv dt will switch to 4 pi r squared dr dt. Finally, once we get that, we're into the substitution step, sub and solve basically. And I remember they gave me a couple givens. They gave dv dt as 5 cubic centimeters per second. They gave me 4 pi. They said when r is 4, so that 4 is going to get squared, but also the centimeter label will get squared. And then dr dt happens to be the only thing that is the variable in our equation, right? It's the only open quantity, so it should be fairly easy to solve this out. I'm going to have 5 cubic centimeters per second is equal to 64 pi centimeters squared dr dt, because this became a 16 times 4, and then divide. I'm going to have 5 cubic centimeters per second divided by 64 pi per centimeter squared, or just centimeters squared. That will equal our dr dt. Centimeters squared into centimeters cubed knock us down to just centimeters per second. And that looks like our answer. So on a test, labels will be important on this particular exam that we do. So make sure that you practice those. I can also say, well, a radius is just a length. It is one-dimensional. D-I-M-E-N. It's one-dimensional, so that would be just straight up a length, not length squared or centimeter squared or anything. Okay, there is a part 2 to this problem. And part 2 says, how fast is the surface area changing? To do surface area, I am going to need a whole nother equation. Pretty much I still have, you have your givens, you can just keep them there. It was 5, and the when was when the radius was 4. And we want to find ds dt, the changing rate of the surface area. So, surface area, you know what, maybe I'll use A. Surface area of a sphere is 4 pi r squared. Let's take the derivative, dA dt. I'm on this step because I got my equation written. The derivative would be 8 pi r dr dt. 2 times the 4 gave me the 8. I can substitute my values, so I have a 5 centimeters cubed per second equals 8 pi. The when spot was when it was 4 centimeters long for a radius, and dr dt. Oh, hold it. I kind of lied. I need to get 2 things in here, right? What was I doing back here, you guys? This is not dA dt, is it? I need dA dt. We need to find dA dt. I was throwing in dV dt. That was dumb. Okay, but I do know dr dt when the radius is 4 because I solved it using the volume equation because I had dV dt. So sometimes if this had been the only question on this problem, I would have come through volume to get to surface area because I would have to be able to find dr dt. So now we're going to use that answer we had from dr dt, which was 5 over 64 pi, as I recall. Yes. Let's simplify our work. Pi's will cancel. This was just in centimeters per second, if I recall. And 8 will go into 64 8 times. 4 will go into 8 2 times. It appears to me that we've got an answer for the rate of change of surface area when the radius strikes 4 centimeters long. And that would be 5 over 2 centimeters times centimeters gets us centimeters squared per second. So sometimes you have to work through an additional one. All right, go to the next example. We are going to go to example 3. I'm going to put it on a new video.